Hello, this is Professor Doug, and we are moving on to Chapter 4 in Hibbler Mechanics of Materials, and this chapter deals with axial load, and we'll be using Excel once again to solve several examples. Now, these examples you will see are more challenging and have more in-depth analysis with Excel, more applications and functionality. So we start to get deeper into the analytics using Excel in this chapter. So let's look at the first example. And our first example is example 4-5 from Hibbler, the 10th edition, and we have a steel rod, A36 steel. So right away you can get the elastic modulus for that steel alloy by looking it up in a table, and we find that it's 200 GPa. And it has a diameter of 10 millimeters. It's fixed to the wall at A, that's on the left here. And there's a gap between the rod and B, and the gap is given as 0.2 millimeters. So then we load the rod axially with 20 kilonewtons along this collar, and there will be, the gap will close, obviously, so there'll be a delta or a lambda B, as you see here in the center, and that will create a reaction at the wall at B, and then there's also going to be an opposite reaction at the wall at A. So we want to find the reactions at A and B. What are they? So we're going to set up our initial conditions, and what I've done is I've tabulated them all here. These are all given, so there's nothing calculated here, but I've converted everything to the newtons and meters and pascals conventional units that we use in analysis of strength of materials. So those are just simple conversions that you can see from this column to this column. All right, everything in newtons, meters, and pascals rather than kilonewtons, millimeters, and gigapascals. Now, we have two unknowns here. We don't know the reactions at A and B. So we're going to, again, use non-zero starter values, and I like to use 1 for a starter value, and then we'll carry this a little bit further. And most of these types of solutions require solving the variables given equilibrium conditions. So we happen to know that FA, the reaction at FA, is pointing to the left, minus the reaction at FB, which is also pointing to the left. So that's minus FA minus FB, plus the load P, which is given, pointing to the right, should equal 0 due to equilibrium. So that's highlighted here in my cursor and mouse. So if we put coefficients before these, we get minus 1 FA minus 1 FB equals, and we bring P over to the other side, minus 20 kilonewtons. So it's minus 20 times 10 to the third newtons. So that equation looks something like this, minus FA minus FB. And it should equal minus 20 times 10 to the third. Right now it equals minus 2. Well, we can ignore that because, again, we assigned non-zero random values to FA and FB. Let's say we put in 10, for example. You can see that our solution is changing, right? So we're going to just leave them at 1 right now. And then we need to use the compatibility load displacement equation. Now, where does this come from? This is in the shaded box here. That comes from a derivation of Hooke's law, and then breaking down each component of Hooke's law, the numerator and denominator. Sigma is force over area, and epsilon in the denominator is lambda, or the change in length, L minus L sub O over L. So these come from prior chapters that we've already worked with, and then we're just rearranging algebraically to get this equation in the box. So AE, if we multiply both sides of this equation, the compatibility equation here, by AE, we get AE times delta, or lambda. And AE delta then is, A is 1/4 pi d squared. D was given. And E is given for steel. We looked it up. And then delta is the gap, was given. So that's 0.002 meters. So everything, again, in newtons, meters, and pascals. And that will work out to this value. Okay, so I have A times E times delta, and A is just 1/4 pi d squared given this diameter right here. So I get basically 100 pi. And that is useful because we know that if we multiply both sides of this compatibility equation by AE, we get AE delta. I'm calling it delta, but it looks like a Greek letter lambda. AE delta, and that's going to be equal to these two terms. The numerators remain. F sub A, L sub AC minus F sub E, L sub CB. So those can be calculated now. F sub A times L sub AC. Well, L sub AC is a constant, and F sub A is unknown. Right now it's 1. And then minus F sub B, also an unknown, times L sub CB. That's a given as a constant. So those will sum up to this amount. However, they should sum to 100 pi. So now we can use solver. So we'll go to data, solver, and we have our pop-up window that comes up. And our objective is to set the sum here in cell B34 equal to 100 pi. So it's 3141.59. By changing the two unknowns in cells B20 and cell B21, which are currently 1, and those are dummy variables, subject to the constraint, we're going to type this in, that cell B25, which is here, this equation of equilibrium, is equal to the minus 20,000, okay, that we previously saw. And those are based on these unknowns too. So I'll just solve, and we get a solution, and here we are. And so there we have it. Our AE delta is equal to the sum of these other terms, which is correct. And our equilibrium equation does sum to minus 20,000. And those are the two reactions at the walls based on applying an axial load to this bar. So that's in newtons, so we're going to convert it to kilonewtons. So FA then is 15.95 kilonewtons. We have a 20 kilonewton applied load to the right, and that means that FB must be 4.05, the difference between the two, 20 minus 4.05, pointing to the left. In this next example, which is 415, we have quite a lot of analysis to do to solve this problem. So this is a post made of Douglas fir. So we can look up the elastic modulus of Douglas fir, a type of hardwood, and that is 13.1 GPa. We look it up in a table. Has a diameter of 100 millimeters, subjected to a load of 20 kilonewtons down. And, that could be a pile driver or some other load-bearing device to drive this pile into, or this post into soil. So it's driven into soil that provides a varying frictional resistance distributed along the length. And that is going to obviously be an equation, and it varies linearly from 4 kilonewtons per meter at the surface, which is 2 meters above the base here. We'll call the base B. And it increases to 12 kilonewtons per meter. So if you've had geotechnical engineering courses, you know that there's more soil friction, frictional resistance with depth. So that's going to be a trapezoid. If you think about the area of that, we have a height of 2 and a base of 4 and another base of 12. So base 1 is 4, and B2, base 2 is 12 kilonewtons per meter, and the height h is 2 meters. So we can actually solve for the area of the trapezoid here quite simply. So what's the resistant force F at the bottom for equilibrium? And what's the displacement of the top of the post A with respect to the bottom B? So it's going to be a small displacement. Neglect the weight of the post. So let's fill in the blanks. The loading forces here begin at 4, end at 12 over a 2-meter depth. And then we have a minus 20 kilonewton downward load here. So everything is converted to newtons and meters in the shaded block. The height y is 2. The diameter of the post is 100 millimeters, so we're going to convert it to meters, and then calculate the area in meters squared by multiplying it simply just by 1/4 pi d squared in meters. So what is the area of the trapezoid? Well, again, it's 1/2 b1 plus b2 times the height. So it's a half of 4 plus 12 times 2. So half of 2 goes away, and 4 plus 12 is 16. So it's 16 kilonewtons, and the meters will cancel in the denominator. So it's just 16,000 newtons. Okay, so we can then easily calculate F upward if we have 20 kilonewtons down, and based on equilibrium conditions, some of the forces in the y direction must be 0. So we have F up plus the trapezoidal area resisting up. You can see that with these arrows, minus 20 kilonewtons down. That means that F has to be 4 kilonewtons. It's just simple subtraction in this case. Okay. All right, good. So now we need a function of this distributed load. So the function of the distributed load then is based on what you see here in this second equation. And that could be calculated for any starting frictional resistance and any ending frictional resistance. And it is a function of y, the height. So this function, for this example, happens to be given as 2y squared plus 4y minus 20. And we need to integrate that function in order to solve this problem. So we're going to use Simpson's quadrature, Simpson's rule, to do that. And what we have to do is set up a column of height from 0 down to 2, okay? And then our load is a function. It's the function. Well, excuse the barking dog. So where were we? We were looking at the p sub y as a function, okay? And that function is, as we said before, 2y squared plus 4y minus 20. So whatever y is from 0 down to 2, we have to square it, multiply by 2, and then add 4 times y, and then subtract 20. So that will, at 0, that's obviously minus 20, which is the downward load. And then at the bottom, it's 4, right? Minus 4. So that is a function. We can just type it in once and copy it down. That's all we have to do. And then we use Simpson's rule, because normally we would have to integrate this function, as you see here, in order to get the displacement lambda or delta A with respect to B over the interval 0 to L. Okay, and L here is the length, 2 meters. So we're integrating the same load displacement equation that we saw in the last example, and we're pulling out 1 over AE as a constant, and we're just simply integrating the function itself from 0 to 2 meters. That's the height, or over this entire y profile with respect to y dy. So we want to solve for lambda a sub b, or delta a sub b in this case. So we use Simpson's rule. Well, if you're unfamiliar with Simpson's rule, there is a link here that is very good. That's a YouTube video by someone else that provides some tutorial. But the way you do it is you set up the vectors of your y and your p sub y, and then we have an interval. Well, our interval between each successive y change in y value here is 0.1. So Simpson's rule, what we have to do is take the interval divided by 3, you can see that up here in the formula bar, and then multiply it by the first term has to be at y0, plus 4 times the second term plus the third term of the p sub y vector. That's it. So you do that, and then you're just copying that, skipping every other entry and copying it down to the bottom, and then just taking the sum of those, and that's simply done here. And I think if I can get that to go away, that would be ideal. So it's a summation here, right, in this case, right, of all of those Simpson's rule quadrature calculations, and we get minus 26.6667. Well, that's not the solution, because that's just the integral over this range. So what we have to do is go back into the equation here and say, well, if we've pulled out 1 over AE, in this integral ahead of it as a constant. So 1 over a times e is just simply 1 divided by the area we calculated times the elastic modulus. Again, everything in pascals or meters squared, that's a constant. And then we're going to multiply that by this Simpson's rule sum, and that's just that. But we're going to multiply by 1,000 because we need to convert to meters, and that's our meters solution. And then now we're going to express it in millimeters because it's a very small displacement. So it's 0.259 millimeters is the solution. All right, so again, Simpson's rule, we need the interval. That's a fixed value. We have to use the relative or absolute cell address with the double dollar signs. We're always going to refer to the same cell here for the interval and divide by 3. And that'll be a constant times the first term plus 4 times the second term plus the third term. And that's how we calculate these Simpson's quadratures. And then we copy it to every other y value, and we will end up with the summation of all of those as being the solution to the integral. That's the solution to the integral. We have to pull the constant 1 over ae outside and multiply that by the integral. And everything must be in the same units. I kept everything in newtons and meters, but then I brought it back to millimeters. So it's a very small displacement. The last problem is another advanced technique, is matrix operations in Excel. So this one is 3 992 steel bars. So again, we could look up the elastic modulus of those if we need to do that. A pin connected to a rigid member. You can see that here. And the applied load on the member is 15 kilonewtons down. You can see that chain here at a distance shown. And determine the force in each bar. And that's axial force. And certain bars have different cross-sectional areas. So those are all given too. So it becomes complex. So we type in the load downward. The areas are given. We convert the load to newtons. And we convert all of the areas that are given from square millimeters to square meters by dividing by 10 to the 6th. The lengths, all of the lengths here are given in the dimensions, so we just type those in of each of these members' lengths and distances from each of these connectors. And then we use our equilibrium equation. So the sum of the forces in the y direction, we have FAB plus FCD plus FEF minus P equals 0. If you want to see that in detail, that's down here. So that's one equation in red, and that's important. And that's just the equilibrium equation for the summation of forces in the y direction. For the rest of the problem, we need to sum moments around C. So summing moments around C, we're referring to this figure B down here. So we have FAB, right? It's going to create a clockwise moment around C times the arm from C to FA, and that's given as, that distance would be AC, so that's 0.4 meters. And then we've got the P, the load downward, right, times the distance from A to C divided by 2 because it's half, so that's just 0.2. That's going to create a counterclockwise moment around C, so that's positive. I'm referring to this equation here. And then we have FEF, which is this load on the right, this reaction on the right, times the arm from C, which is 0.4. So those all have to sum to 0. So you can rewrite that like so. I just move the PAC over 2 to the right. Now it's negative. And I have a AC, a CD, and a CF term, and my CD term is 0 because we go right through point C when we sum the moment. So then the last, that's in blue. The last equilibrium equation is from figure 3, which is over here, load displacement relationship. And we've seen that before, FL over EA, and that's going to give us our delta or lambda. And that, based on this cutaway diagram, if we fill in all of the values, we get FC equals 0.3 FA plus 0.3 FEE. And then what we're going to do is just set that up so that we have a standard form equation that's going to sum to 0. Okay? So we have all of our terms. We have all of our equations. There's red, blue, and green are 3 equilibrium equations, and I've set those up in a matrix of force coefficients. So all the coefficients ahead of the f's here are 1, and the solution to this equation is minus p. Well, minus p is going to be 15 in this case because it's already negative, so minus a negative is going to be a positive. And then for the blue equation here, our coefficients are a sub c, which is minus a sub c, minus 4, and then 0, fc sub d, and then ce is plus 0.4, so that's here. So I don't know the unknowns, fab, fcd, and fef. We've got 3 equations, 3 unknowns, and so we're using matrix operations to solve this. And then in the green equation here, I have 0.3 FA, this is just the coefficients, minus 1 FCD, and plus 0.3 FEF. Now they all have to be in the same order, so you put your FAs first, your FCs second, and your FEs third. And if there is no FC, then you put a 0, like in this case, in the blue equation. So those are my force coefficients. So then I know my resultants of each of these equations. The first one is 0. I'm sorry, it's P, so that goes to the other side because it was negative here, so it's going to be 15. The second one is a minus P times AC over 2. Well, AC over 2 is 0.2, and minus P is minus 15, so I'm multiplying that by AC over 2, which will result in a minus 3. And then the last equation, my resultant of that to the right of the equal sign is 0. So these resultants are all the values to the right of the equal sign, and they're constants, okay? Because a constant load and constant distances. And our force coefficients are the coefficients ahead of the 3 unknowns in front of them. So what we can do is take inverse of the first matrix, that's matrix here, and we use enter the matrix A in a cell block, select an output range. Here's my output range that's highlighted, and just type M inverse, matrix inverse, and then the cells that I'm going to calculate it for. So here it's G26 through I28. It's just like this span. And then here's the equation, and there it is, M inverse. And then that will populate this matrix with the inverse matrix of the force coefficient matrix. I've got my resultants matrix, which we knew were constants. Now all I have to do is perform matrix multiplication in Excel. So you're entering matrix A in a 3 cell block and vector B in a 3 by 3. A is 3 by 3, that's this matrix. B is 3 by 1, that's this matrix. So it goes rows and columns, right? And then select the output range, which is this 3 by 1. And then you type in M mult, which is matrix multiplication. And here are my 2 matrices that I'm multiplying. This first one times this one. This is a 3 by 3, and this is a 3 by 1. I get a 3 by 1 result, and here are my results. So I'm done, and I solve the problem using matrix multiplication in Excel. So it's a more advanced technique, but very useful, especially where we have 3 equations, 3 unknowns. We could solve this by substitution or some other way, or using solver as well, but we wanted to show the versatility of Excel here. And then in the last example, let's just skip back to that to show you how we use Simpson's rule for integrating a function. And then in the prior example, the first example we saw was utilized to show the calculations using solver. So this chapter in axial loading has a lot of versatility to use multiple functionality in Excel to solve the complex problems with multiple unknowns.